Hi guys! This video is the first part of a three-part lecture on the topic area of a plane region and arc length. If you have not yet watched the previous two lectures, I suggest you do that first. Now without further ado, let's begin. For today's video, we have two main topics. The first one is the generalization of the area problem that we have before. Our second topic will be on arc length. Now before we go to the topic of area, let's have a short recall. Now consider that I have these two rectangles and I wish to find out their areas. Now we know that the area of a rectangle is given by its length times its width. Now for simplicity, I will always suppose that the width will be the length of the shorter side. Now let us analyze and find out how to get the areas of these two rectangles. Let's consider first the green rectangle. Now we will call this rectangle a vertical rectangle because of its orientation. To get its area, let's first find its height. Now the height can be obtained in two ways. First one is by counting. I have a 0 here, and then I have a 1, 2, 3, 4, 5. Clearly, the height will be equal to 5. But another way to do that is by noting that the length from this point to this point is just the difference of the value here, which is a 5, and the value here, which is a 0. A very important thing to note is that the 5 and the 0 are both values of y, and that the height here is just a change in y. On the other hand, the width, which is the length of the shorter side, can be also obtained by counting 1, 2 to give me a width of 2, or it can be done again by subtracting by getting the value 2 minus the value 0. And contrary to the change of y before, the width will now be a change in x. And since the area will just be a height times the width, that will be a delta y times delta x, and that will be just a value of 10. On the other hand, for the blue rectangle, we will be calling this a horizontal rectangle because of its orientation. Again, for its height, which will be this horizontal length here, it will be just a negative 5. And I got that 5 because I have the value here at 0 minus negative 5. It's very clear that this is still a change in an x because this is a change in x values. And turns out to find the change in x, the way to do that is to obtain the value of x on the right minus the value of x on the left. In this case, a 0 minus negative 5. On the other hand, for the width, which is again equal to 2, to obtain it will just be again a 0 minus negative 2, and that's a delta y. And to get the values of delta y, it's just the value of y at the top minus the value of y at the bottom. The area, which will still be a delta x now times delta y, is equal to 10. What this slide is being taught is that first, when you have a vertical rectangle, the width, which is the important value here, is in x, while for a horizontal, its width is in y. Again, for vertical, it's in x. For a horizontal, it's in y. The second one is that when you have a width and a height, there will be changes of two different variables. And that is if one is delta x, the other one is delta y. If one is delta y, the other one will be a delta x. Another one is that to get a change in an x, it's basically just a right minus left, and a change in y is just a top minus bottom. And last but not the least is that the area for these types of rectangle, vertical and horizontal rectangles, it will always be a product of a change in an x and a change in a y. Now these concepts will be repetitively stated all throughout this topic, so it's very important that we take note of it. Now let's start with area. Let's recall that the definite integral that we have before is basically the limit of a Riemann sum. And this Riemann sum is just the sum of this quantity here, which is the height of the rectangle, times delta x, which is its width. Ergo, this is just the limit of a sum of areas of rectangles. And it's not surprising that if we see that f is a positive, will always be positive for the whole interval AB. The integral, which is the limit of a sum, will give you what we call the area under the curve, or in general terms, the net side area. Now, the question is, what will happen if I have a y equal to f of x at the top, but the bottom part does not lie on the x-axis? For example, this case. So you will see this is now an area not just below y equal to f of x, but also above y equal to g of x. For this case, we can still use the technique of partitioning our area into rectangles and then getting its limit, but there will be some changes. Let's try to find out how to get the area of this using the technique of partitioning. First part will be I will be dividing our interval AB into n equal subintervals. Notice here that I have a vertical rectangle, and that's the reason why the width will be in x. Again, for vertical, it's in x. For horizontal, it will be in y. I will be also obtaining a random point x sub I here, which I will be using to evaluate my function f of x and later on g of x. Because the main goal is to find the area of this dark green rectangle. Since I already know the width, which is a delta x, I just need to find out the height. And the height of the rectangle will be a delta y. Since the y value here is equal to f of x, by evaluating at xi, I'll get the y value here. And then since the y value here is equal to g of x, I will be able to get the y value here by evaluating g at xi. And thus, top minus bottom will give me the height of my rectangle. And that tells you that the area of my rectangle will just be the height times the width, and that will be given by this. If I sum it all up, I will have an approximate value for the area of R. This is still an approximate because of the holes here in the excess values like this. If I want to get the correct estimate for my area, I will get its limit. And that is what we will be calling the area between two curves. Let us have that definition. If f and g are continuous functions on my interval AB, and f is greater than or equal to g of x for all x in AB, it means that the graph of y equal to f of x is above the graph of y equal to g of x. Then that means that the area bounded by the region above by y equal to f of x and below by y equal to g of x between x equal to a and x equal to b will be given by this formula. This formula is a formula for area. And what I need here are the values a and b, f of x, and g of x. Now there are a lot of ways to memorize this formula, but we'll be giving another mnemonic for it so that we will be able to generalize it easier next time. And that's this. We can think of an area of a region as an integral of h dx because remember what we need to find out here is the height and AB. AB here is just the interval I covered by the region along the x-axis, and h will be our height. In this case, the h that we'll be using is f of x minus g of x. Of course, dx here is the width, and in an integral, the dx tells us the variable that we will be using. A very good observation here is that the dx here tells you the variable will be x. The quantities here are also in x, and AB are also values in the x-axis. So all parts of my integral are in terms of x. Now, since this will be a very important part of our study, I will be placing it on the left side of the screen so for reference later on. Now, let's have an example to demonstrate this. I want to find the area of the region bounded by y equal to x cubed, the x-axis, and x equal to negative 2. So what do we need? If you refer to the left side of the screen, what we need are A, B, F, and G. Now, clearly by the problem, we don't know what they are. One way to find them, well, not one way, but the first thing to do is to draw the region first. Drawing the region will tell us what the A and B are. At the same time, it will tell you what F and G are. Remember, to know what f and g means to know what is the function above and what is the function below. Now, given below is the drawing of our region, where y equal to x cubed will be this curve here that I am tracing currently. Of course, I have the x-axis, which is this axis here, and the vertical line x equal to negative 2. Now we can now proceed to finding out my interval. So to find the interval, I need to know all the x values that will be considered in my region. For example, since this point here is part of the region, then that means the x value should be also part of my interval. This is a part of the region, so there is also an x value there. So what I'll do is I'll go to the leftmost part of my region, and then I'll trace it down, and I'll notice that it's negative 2. Negative 2 will be the lowest value of x considered, while the highest value of x considered will be in this case 0. So that will give me my interval negative 2 to 0. So I was able to do that by just tracing out the leftmost x and the rightmost x, the smallest and the biggest x's. For f and g, it's very important to know the orientation, what is above and what is below. Now, if you go back to the definition as we have before, to get the f, it should be equal to a y value. So, for example, in our problem here, if I want to know what the f is, I need to know what is above, and then I need to know the y value there. Now, obviously, the curve the bounding curve above is the x-axis. But I cannot put the x-axis as f. So I will look at the equation form of the x-axis, and that is just y equal to 0. Since y is 0, then the f will be the 0. Well, the bottom function here, the bound below, will be y equal to x cubed, and that means the isolation x cubed will be my g of x. And that gives me my function 0 minus x cubed equal to negative x cubed. You will see here that by isolating the y, the h here will be all in terms of x. And thus, by plugging it in our integral, that will be from negative 2 to 0, negative x cubed dx, anti-differentiating and then evaluating, you will obtain the value 4. A very good question here is that, why is it that I have a positive answer when the region that I am talking about is below the x-axis? The reason for that is because the function that we have here, which is h, f of x minus g of x, in the derivation, this is a formula for area, not net sign area. For one, if I, for example, ignore g of x, f of x can be a negative number. But because f will always be bigger or equal to g of x, the difference f of x minus g of x is always greater than or equal to 0, and thus telling me that the integral will also be positive, or at most, non-negative. It's very important here that we check our answers at every instance, because the moment that the answer will be a negative number means that we are doing something wrong. Now let's have another example. For example, I want to find the area of this region bounded by y equal to 2 minus x squared and y equal to negative x, given that I have already drawn the figure. An important skill here is to identify what curve is to what equation. So for example, y equal to 2 minus x squared is clearly a parabola, so it's this downward facing parabola, while y equal to negative x is just this negatively sloped line. Though we have a drawing, this is not enough. For example, in finding the interval, I can say that the leftmost part happened at this point here. However, I don't know the x value there. And the rightmost part happened at this point here, but I don't also know the x value here. So I need to find out those two points so that I can evaluate it properly. And if I observe it well, these 2 points are exactly the points of intersection. So by getting the points of intersection, I will be able to find out that there are 2 points of intersection here, one at -1 and another at 2, thus giving me the interval that I need. And thus, the area will just be from -1 to 2. Now, since I already know the orientation, which is above and which is below, I just need to plug it up. The y value at this curve is 2 minus x squared, and the y value at the line will be a -x. And of course, I will never forget the dx. Simplifying this and then anti-differentiating, and using FDOC, I will be able to get this quantity, which is a positive number as I have indicated before. Now let's have a short summary of what happened here. One of the most important parts here will be the f of x minus g of x. And as I've said before, in this variable x, since we are using a variable x, the height will be a change in the other variable y. And that is, you know what f and g are by expressing your curves as y equal to f of x, y equal to g of x, and knowing which one is the upper function and which one is the lower function. Because once you know that, the height is just upper function minus the lower function. Or the function given by the curve bounding above, minus the function that's governing the bound below. However, a very important note here is that the h should be true for the whole AB. And that means what is above should always be above, and what is below should always be below. And that is true for the whole AB. Because the moment that this is not the same for the whole AB, we need to what we call divide the region. And that is, I will be dividing my interval in such a way that for each sub-interval, what is above is always above, what is below is always below. Let's have an example for that. I want to find the area that is being bound by the graphs of y equal to sine and y equal to cosine. Cosine here is the dark blue curve which I am tracing right now, while sine is the light blue one that I am also tracing right now. Okay, I'll be doing that from 0 to 2 pi, and you will see that sometimes cosine is above and sometimes cosine is below, and it will again go above. This is a prime example of a case where what is above is not always above, and what is below is not always below. In this case, they are switching. Now to solve this, what I will be doing is I will be tracing it. For example, from 0 until this part here, cosine is above. But at this point, it's a point of change. From cosine, sine is now above this region here. And then at this point here, there will be another switch, and what is above will now be cosine again. For the one below, you will see that the points of change where the top functions switched happens at exactly the times when the bottom functions switches. So what this means is that I need to find out the value of x where this switch happened. And just like in the previous example, uh, you will observe that it is the points of intersection where it switched. So I need to find out what the points of intersection of y equal to sine, y equal to cosine x are. I'll be able to do that by just solving for the quantities, and it will be left as an exercise to show that from 0 to 2 pi, it is at pi over 4 and 5 pi over 4 that these two curves intersected. And that tells me that to get the area, I just need to get the area of this R1 plus area of R2 plus area of R3. R1 will be from 0 to pi over 4. Now to get the height, I just need to know what is above and what is below. Clearly, what is above here is cosine x, and what is below is sine x. Of course, I will not forget the dx because that completes my integral. For R2, it will be from pi over 4 until 5 pi over 4. And in here, what is above is sine, and what is below is cosine. Of course, I also still not forget the dx because that's very important. And for the last region, it will be from 5 pi over 4 to 2 pi, where what is above is cosine and what is below is sine x. Simplifying this, you will obtain a fourth square root of 2. What we learned here is that it's important to know where the split happened and if it does happen. One good way to do that is by tracing, just like what I did before. I trace the upper function, and whenever I have a point where the upper function changed, I'll need to split it there. Even if the bottom function does not change, as long as the upper function change, it's already a moment of split. I will do that until the end for the upper, and I'll also do that for the bottom function. Of course, for this example, where the upper function changed, the bottom changed as well. This is not always the case. For example, if I want to find the area of this gray region here, you will see that I have three curves. The first one, y is equal to x squared. That is the blue parabola facing up. Y equal to 2x is a line, and 7x plus 4y equal to 15 is also a line. So how do I know which lines are which? We will do that by looking at their slope. Since y equal to 2x is a positive slope, then that means we are only left with this red line which has a positive slope. While this one, you will find out that this has a negative slope, so it will be the green line. Now, just like before, though we are given the region here, we need to also find out the points that are necessary. For example, I don't know what point this is, and thus not knowing where the x values I will be considering start at. I also don't know this one, which is the rightmost x. And if we ask ourselves, do we need to split my integral? The answer for that is yes. Because the upper function, if you trace it from the green curve, it switched at this point here to become a red curve. So that means the upper function changed, and I need to know what this point is. For the blue curve, which is the lower curve, you will see from the start until the end, it does not change. So this at this point here, only the upper function changed, but nonetheless, we need to split it there since something changed, either above or below. So to be able to find the x's, we will be again finding the points of intersection. So first, I will get the points of intersection of C1 and C3. That's the blue parabola. And C3 will be this green line here. There are 2 points here, -3 and 5/4. Not all points of intersection are important. For example, the -3 is important because it is this point here, the starting x. But 5/4 is a point somewhere here, which we actually don't really need. So we need to pick well what to use. For C2 and C3, that will be the intersection of these two lines. There will be only a single point here. We need it because that's the point of change, a point of splitting, and that's at x equal to 1. And last but not the least, for C1 and C2, which is the parabola and the red line, there are also 2 points of intersection, 0 and 2. And you can guess, the important point here is 2, because that's the rightmost x, while 0 will be a point here which we actually don't need. And thus, the area is just the sum of the area of R1 and the area of R2. For R1, the x values start at this one, which is, as I have said before, it's -3. And it ended at this red line here, which is at 1. At this full region R1, the top function will be the green one. And you will notice here that the green one is this line 7x plus 4y equal to 15. We cannot put it here. We cannot place 7x plus 4y equal to 15. For one, the function here should be an expression and not an equation. So what we will be doing is, as you may remember, this should be a change in y. So I will isolate y, transpose 7x, divide by 4, and thus y will be equal to 15 minus 7x over 4. So it's the isolation of y that you place here. Minus, the bottom curve is y equal to x squared. So I will place here minus the isolation of the y of the bottom curve, and that is x squared. Of course, I don't forget the dx because that's an important part as well. I will also have the second one, which is now from 1 to 2. And then, just like before, the top function here is y equal to 2x. Since 2x is already isolated, I'll already just put 2x here. X squared is also isolated. So I'll have the bottom function x squared. And you will see that the bottom function did not change, as we have seen before. It is only the upper function, the first parts, that changed, and we see that in our setup. Of course, you can solve this, whose answer will be 40 over 3 square units. Now, you will see here that our solving for area is divided into three main parts. The first part is finding all the pertinent information that we will be needing. This includes drawing the diagram to know the orientation of my curves, and also finding the important points, namely the points of intersection, and later on, the vertices. So vertices of parabolas are also important points. The next part is setting it up, finding out what A and B are, finding if you're going to split it, and lastly, finding out what F and G are for particular intervals. And last but not the least, we'll be using the fundamental theorem of calculus and other techniques to evaluate our integral. Most of the time, we do not do the third part anymore since it is on a previous topic. But in real life, of course, you will need to answer it on your own. Now that ends our first part. In the next part, we will be offering an alternative solution for these types of setting up of areas. And on our last part, we will be dealing with arc length. I hope to see you in our next video.